Oh boy. The octopus video was actually when I look at the octopus video, I think there are a couple ways of what they said. Like the script wasn't proof checked so that you actually have a proper coherent and um non-repeating set of information. It's like my videos scrambled, not thought of well. As you can see, I've gone through about half of this video, um, and it's
in a
bothering.
non-classical state.
It's bothering me as usual for a couple of reasons. We'll get to that.
Thank you to Brilliant for supporting PBS. Some things really do seem to be impossible, like faster than light communication or breaking the.
Okay, fast and light communication can still happen because light is not special, and you can just, as much as you can go faster than sound, there are mechanisms for going faster than light when it comes to signals, but it involves an entirely different atmosphere than what we expect, which they already did those experiments over 100 years ago. Disappointing.
Law of thermodynamics, or learning the second law and not being forever haunted by the whisper of the heat death.
Okay, if I were to go on to a tangent about the second law of thermodynamics and the whole thing about stuff is gonna do whatever, um, I recently came up with a basic, or not recently, I recently made a video about how I got no clue how long ago I thought of. At some point, I heard about the idea of the ability to split quarks away from each other, and then you end up with new quarks. So I devised a atomic tuning fork so that if you have a frequency applied, it will wobble doing the splitting, and then the some quarks will be held and push away the other quarks. It was a very precise setup, and I assumed that with a genuine, like a friggin' tiny nanometer cube, and 20% of that cube devoted to the stuff needed to control the quarks. Um, 1 nanometer cube of this tuning fork stuff can then excite the quarks, making the new quarks, and then you can just like shake the tree a bunch and get a bunch of apples to drop out of the sky, randomly generating matter out of what appears to be nothing, but is in effect, we can in fact say it does happen. It's just it would take a lot of power to do so, but there are ways of making that still happen, and making vibrations at the exact frequency. Um, a tone emitter can just be hitting that tuning fork sort of thing, and then boom, you just have it constantly emitting quarks. Then those quarks need to be absorbed, and then you can turn it into hydrogen, and then you're making a cubic meter of hydrogen, so you need it in a giant box, and that's every second, approximately. Like, it's just farting out quarks rapidly. Um, It's crazy powerful. So the thing is, if you could just keep on making that thing work, you're going to be generating so much mass eventually that if you had a big enough one, you could power a rocket or fill a rocket full of fuel and then go with that. And with some refinement, you can turn the stuff into oxygen to enhance the fuel
Yeah.
and what literally do whatever you want with it. But I went into very far detail in the other videos. So the point is, if you can make hydrogen out of basically nothing and then shunt that into a star, a system the size of a couple of moons would be able to replenish a star um, generously. Um, so you could just put in the light elements and take out the heavy elements from the star, and then you have a constant stream of heavy stuff and all of the light stuff you shove into it. Um, it would be able to help the star be more stable and last for a few more billion years every time you do this cycle, and you only need to do it every few billion years. So, perpetual motion and the ability to avoid the heat death of the universe. If you have a planet-sized generator of this type, you should, or a planet-sized like equivalent, which wouldn't be a planet in shape, but it would be a planet in the amount of stuff you need required to make this thing work. You can easily provide enough more new material to fill in multiple stars. And then on top of that, all of the rest of the material that you're not using in between every billions of years of need to replenish um, can be used to make brand new stars. Um, and then you could technically fill the entire galaxy with a planet-sized generator. It doesn't matter. Also, you could easily make entire um, sections of the galaxy devoted towards generating new hydrogen out of quarks, vibration induced split and division and uh, the restructure of new quarks. Like this process can be just mass produced so that you can have an entire galaxy be self-sustained and power your power plants without any amount of strain whatsoever. It's an infinite supply. The main thing is the amount of power that is required, the amount of upkeep, and whatever else. And of course, right now, 2026, we are not at the level of making that kind of technology possible but we just recently did things with shaking electrons the right way so that they make the 1 quadrillion frames per second image that we're capable of using now. And that's the level we're at. And that's amazing. And that's basically where we need to be in order to have, um, we need to be that rapid in order to work this quark situation, but we need to be way more intense. But imagine changing from an optics thing to then having a vibration generator that is so powerful that you're just creating matter And the thing is, you don't need to have a nanoscopic size little particle generator. That's what it takes to do one, and that fills up an entire cubic meter every second. No, it gets worse because you can have an entire sheet of this material and multiple sheets that are layered on top of each other. So you have an entire cube of this material, and then that would fill an entire, um, a vastly much larger area full of quarks. So the problem with the scale of this system is that if you go too big, you are more likely to lose quarks. The smaller you go for each system that is able to then capture the quarks, fuse them in a way that gives you protons, and then fuse them in a way that gives you um, neutrons as well, like mute, what is it, degrade them into neutrons, um, or add what you need to add to make the neutrons. And then also using gamma rays to make the electrons, you could just make energy conversion into basic elements simply. So that's very Star Trek, and it's great, and it's real. It's just we're talking basic elements right now. And then after that, you can then use those elements. Well, technically, you don't need. Here's the thing: stop thinking about adding electrons. You don't need to do that. Keep the electrons out of the loop, and you can make whatever. At that point, you can make whatever material out of whatever size, and use sound standing waves to control the shape of whatever it is you want to make. Then spray in the electrons. They make whatever you just molded solidify into whatever type of thing you wanted to make. Sound is really going to revolutionize the universe. Yeah, Doctor Who would be pleased. But I mean, it's true because you can make the sound control or hold at the extreme frequencies you need that are so tiny that it's actually really easy to make these sounds. We already have emitters that can do that. The thing is, um, yeah, with these specific sounds, you can control each individual proton and neutron to make the structures that you need to make atoms as whatever size, whatever type of atoms you want. Just mass produce uranium or neutronium or anything that you want. It's crazy how real that technology is. It's just that we're only now realizing sound is a very important component, which is ironic because we already had that information. I'm really wondering why people aren't on this already. Anyway, suffices to say the heat death of the universe is not, it's not going to happen. We're going to think that we would not learn how to manipulate matter perfectly using outer sound or energy-based sound waves. It doesn't have energy-based wave systems. We don't need sound exactly. We need waves, and EM field is waves. So all we need is EM field-based waves technically. But sound might be like physical audio sound might be the thing that we can use to be like pinpoint tweezers to make the stuff. The point is, we will get there. Heat death of the universe won't happen, and eventually we will be not only sustainable, but like look at 6 trillion years in the future, and we have a more dense, bigger. The problem is we're going to have a more dense and bigger universe more stuff in the universe than we ever had when we started. Like, imagine for every billion years, you now have a new galaxy that you can just poop out of your factory. This is what will happen. Um, and it's just barely scratched the surface of how, but who's going to be making galaxies anytime soon?
The universe seems to conspire to thwart any attempt to do certain things. And for a while, it seemed like the quantum structure of spacetime might be part of this forbidden knowledge. But now, researchers found ways to trick the universe into revealing its quantum underbelly. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to watch our composition of ordinary matter. The UV glow Kerr rotating block of space-time seems fundamentally impossible. But we also saw that there are
Here's the thing about this whole method of using a single beam. Why would you not use multiple beams? It's just refraction and reflection. You can split the beam into multiple beams and then have all of them in a gigantic array, like a whole wall of beams in both directions, as well as a grid of beams on the ground. So you can have an entire three-dimensional map space that takes in every bit of information that you can of the gravitational wave effect. And this kind of sensor is genuinely, you don't have to have something as big as what they did with LIGO. You could do LiDAR or whatever it is. Lego?
the methods that are just so stupidly difficult they might as well be impossible. They seem to involve using planet-sized graviton detectors and even stellar corpses as...
You realize gravity is just permeating everything. So you're going to end up with nearby gravity distortion. All the different planets in your solar system are going to have gravity effects on everything that you could detect if you had the right stuff to detect it, besides, like, explosions of stars or what have you, which are more violent, but like the more subtle stuff is still out there to be noticed, and then you could just pick that up. Anyway, and the main thing about having a very sensitive detector, you don't need that. You could just make a very takes in all information detector and then shove that into an AI that can then take out all the noise, or any algorithm that can take out and disperse every bit of noise on every bit of frequency, and then cross-reference for like literally anything. And it's scary because it reminds me of Batman 2, where you use the sound to make the echolocation to find Joker. Only we can just do this anywhere. One detector can find a lot of information about the area around it. Ironically, not everything about the planet was detected with LIGO, and I'm very confused about that, because why wouldn't it be? Like, literally, you should know things about any part of, like, the hemisphere that is surrounding you and your detector. Maybe not everything on the other half of the planet in relation to your position on the planet, but it should be possible to have, like, a gigantic net that can just know everything about everything. And if you had these everywhere, well, you could cross-reference all of those bits of information everywhere else to have even larger, constantly running um, detection grids. The other thing is you could have something more simple where it just needs to be wires. Like lasers are one thing, but little disturbances in wires and the transmission could also be used as like just a gigantic antenna, knowing about all the stuff that's passing through it, and the gravity bump is like it's a lot easier than you think to make a big detector of the entire planet. You just need a gigantic coil of wire, which we already have as the electrical grid, which we could technically be scanning the entire electrical grid of the planet to then know things about all sorts of stuff that can affect. There would be a ton of noise to get through, but instead of using like the lasers, which is more predicted, like you could end up noticing there's just all sorts of other stuff that you have to filter out. They're just more filters to put on, but it could happen, and then you have trillions of terabytes of information to sift through and know everything about the entire planet all simultaneously, including what your mom did yesterday. I had nothing to do with that, okay?
Graviton sources. Sounds disheartening. Well, maybe we have to wait millennia until we can build our astro-engineering superstructures, or maybe we can just get cleverer today. In recent years, theoretical and experimental developments have made it possible to conjure up new ideas for detectors. One such possibility is the use of quantum sensing, outlined in a paper by Tobar, Merkanden, Badel, and Pikovsky, submitted to Nature in 2024. In the previous episode, we talked about a family of experiments that work by treating the graviton as any other particle. So rather than trying to detect its infinitesimal gravitational field, we instead try to spot a more direct interaction with another particle, similar to how we do with particle colliders. When we account for the extreme low probability of such an event, we found that we needed these planet-sized detectors and stellar graviton sources to even have a remote chance at it.
So, the thing that people are still not grasping, again, is the EM field fluid is everywhere concept, which is like we should know this, but is not the case. So you got to ask yourself, first of all, what is the thing that gravity waves are able to travel through and interact with and send that information across the galaxy to us in the first place? Getting through our atmosphere and just going straight to us. What's the thing that's in common in outer space and in an atmosphere? Again, it's the EM field. So we're not thinking in those terms yet, or they're not. I already have been for a while. I talk about the double slit experiment and the whole thing about the EM field being part of directly what is causing the stuff, the interference pattern. So all of that is that electromagnetic field being everywhere, and it's a fluid, and it's the thing that is transmitting all this information and stuff. It's a lot simpler to just monitor the entire EM field, multiple bandwidth, multiple like layers of frequency, and eventually this video is going to talk about different sized materials to gain information on different events. And I'm like, well, why don't you just make a spectrum machine looking at all different types of materials and things that give you this resolution of information?
In order to claim that we saw a quantum of gravity, these sorts of detectors require that the graviton interact with another quantum particle. Now, elementary quantum particles are tiny and gravity is incredibly weak. Combine these two, and the graviton has only a minuscule chance of having a sufficiently head-on.
Just imagine any kind of sound. You're having a wave pass through everything and be heard through the entire room. So you're not looking for individual detections, you're looking for the ripples. And the ripples are through any matter whatsoever, and the ripples are mostly in the electromagnetic spectrum, but again, that can be directed to any amount of matter that you have.
Collision with such a particle to produce the sort of interactions that we need. Now, we
So far behind.
can't do much about the weakness of gravity, but what if we can make a quantum particle bigger? What if we could make one that's human scale, that's macroscopic? That's what this new paper proposes with its resonant mass detector. It'd work like this. Cool a metal cylinder to as close as possible to absolute zero. In that state, there's almost no motion in the individual atoms in the crystal lattice. There's also almost no energy in the global oscillations of the metal in its vibrational modes. At sufficiently low temperature, those vibrational modes are quantum states. They increase in discrete steps, quantum jumps, just as an electron jumps up in discrete energy levels in an atom.
Okay.
These individual quantum vibrational modes are called phonons. They're like a quantum of sound. Now, these are going to be our macroscopic quantum particles, these phonons, and they will have a vastly larger cross-section or probability for interaction with the graviton than does a single electron. So, when a graviton passes by, there's a tiny but no longer unthinkably tiny chance that it'll excite a phonon. Then, using quantum sensing techniques, this phonon can in principle be detected. And that could be considered the detection of a graviton. There are, of course, one or two complications. To even get our cylinder into its vibrational ground state, it needs to be cooled to a small fraction of a single Kelvin, and I'll come back to the exact number and the plausibility.
Again, when you're thinking about a gravitational wave event, you're thinking about something the size of a planet, a black hole, a star, doing a kind of shake that genuinely it would take a very large, like it's why LIGO is so freaking large, and that's still only a partial detector. It's very basic and it's very simple, and yeah, it's great and it accomplished things, but it's also a very like bare bones, the primitive, the most limited, the most like even for its size, it's still very like simple in its construction, with a single beam being oscillated and stuff. And if you notice the rippling through it, and as the ripple then stretches out to different parts of the beam, you can tell the shape of the ripple and these things. And with 2 directions of the ripple being noticeable, there is only so much information you can gain from that. It's outrageous how tiny LIGO really is compared to a gravitational wave event. However, again, you're talking about a giant swath of distortion of all things It is basic. Gravity waves are basically just gigantic sound, and that's really all that they are. So all you need is some kind of microphone big enough that this big sound is going to then pick it up. And so that's what they've approached it with.
Ability later. But even having achieved that, most of the phonons generated in the detector will not be due to gravitons. The excitation energy of a single phonon is so small that any source of noise can produce one. That includes the thermal fluctuations that we are trying to minimize, but also seismic noise, cosmic rays, electromagnetic interference, internal material defects, and feedback from the device that we're using to measure these phonons.
I mean, if you understand the shape of a gravitational wave effect, then you can understand that a ripple in the area, so as some parts of the system progress, you end up with this trough that is noticeable, detectable, and easily recordable over the entire area of a detection system, not a tiny little particle that's useless. You're not looking for a single thing. You're looking for a vast ocean ripple. That's the size that we're working with, is a freaking ocean tidal wave type of effect. That when it hits, you're going to know, like, okay, was it a basically straight line with a tiny amount of swiv in it? And it's like that swiv equals it came from whatever direction, it was a bump, and whatever else. And as those things progress and change and evolve over time, they explain the entire event from whatever thing that happened. It is quintillions of data points, which could be um, seen as like a gigantic sound wave vibration. It is not a single item that we're looking for. That that most certainly is directly just not what we will ever hope to find. Single items are pointless and nothing to do with gravitons whatsoever.
Try as hard as we might, it's not
Or
feasible to reduce
gravitational waves.
noise to the level that gravitons are the main source of detected phonons. But what if somehow we had an independent way to know that a sudden flood of gravitons had passed by our detector at the very instant that a graviton was detected? And we knew that those gravitons were of the exact frequency as our excited phonon. Well, assuming that we got our noise down low enough, that would probably give us a lot more confidence that we'd actually succeed.
Understand the noise is not just changed in the structure of the material of the detector itself, but filters in the system designed to understand like all the different types of things that can influence all of the sound that is being detected, and then you just pull all of those out. Like, you know, this thing caused that and this thing caused that. They've made videos about it. It's like, oh, we can find out this is the sound of a car rumbling by. This is the sound of your footsteps as you were going through. These are all these other things that we can pull out, and then what was left in the information, right? The detector doesn't have the ability to discriminate. It can't. So instead, you just take in the shit ton of information and you search through all of it for everything that we can rule out, and then what's left is gravitational waves.
succeeded in detecting a graviton. And this is the other brilliant part of this proposal. We actually have a way of doing just that. In 2015, we detected our first gravitational wave from merging black holes with LIGO. Since then, we've detected hundreds. If gravitons are real, then a gravitational wave really is just a coherent flood of many gravitons, similar to how a laser is a coherent beam of photons. A gravitational wave from...
Okay, again, if you think of the electromagnetic field spectrum, a wave and a jolt in the field can make these effects that spread out. You don't need gravitons to do it, you just need to witness any matter whatsoever, and you get these interactions. Assuming that there is some kind of graviton, again, you don't need it, you just have the EM field and you know all of it. So technically, there are many other ways to make a gravity wave detector. It's just so much simpler than this.
A black hole merger might contain 10 to the power of 36 gravitons, and those gravitons will share the same well-defined frequency.
10 to the power of 36, what is that number? Well, we start by dividing it by 3. So 36 goes into 3 12 times. So that would be, instead of, if million is 2 sets of zeros, this would be 11 whatever the actual word for that is.
As the gravitational wave that they're part of. Now, this is starting to all come together.
When you imagine your dream business...
I don't.
Frequency equal to an expected gravitational wave frequency. For a neutron star merger, like the ones we've seen with LIGO, a possible candidate would be a beryllium bar of about 15 kilograms. Alternatively, to detect a graviton from a black hole merger, a niobium bar weighing around 10 tons would have the right properties to be excited by a graviton with the right frequency, around 175 hertz. The bar would then have to be cooled to 1 millikelvin. Now, this is colder than what we are currently able to achieve. At best, we can manage a few hundred millikelvin. Proposed experiments get us a bit closer, so this might be viable in the near future. Once the cylinder is attached to our phonon detector, we'll start to get frequent clicks of detection. Now, almost all of these will be due to the various sources of noise, but eventually an excitation will occur at the exact same time that LIGO detects a gravitational wave of the same frequency. And as long as the noisy excitations are rare enough that such a coincident detection is unlikely, then we can hope that we've actually detected a graviton.
Right.
And this brings me to the other main hurdle: continually measuring what would be an extremely delicate system without ruining the precision of the measurement or the quantum state. Since we don't know when a gravitational wave is going to hit us, the experiment needs to run continuously, and it needs to very weakly monitor the cylinder, checking for an excitation. We're also not there yet with the quantum sensing technology needed to do the delicate continuous monitoring, but it's something that
I remember someone making a billion frames per second camera in their garage using an oscilloscope, because that was able to discriminate all the electrical signals and then input that into raw data. So essentially, you can make similar sensing systems that have as many oscilloscopes as you want to put into it, and then they can just be running and gathering all that information and translating it into a format, maybe 3D printing the shape, or just having a 3D base model to apply all those bits of information onto the program to essentially, like, the literal best way that you'd ever want to do this is like have all the information be translated constantly, and then as it's being translated into the different possible noise things and the stuff that you can assume is part of the stuff, all the other extra stuff will show up in that data like a freaking firework, because it'll be like boom, and then you get that, and it's like combined with um, other sensory equipment to get rid of the noise. You could have just record any anomalous information while the detecting system is constant and can just run forever. You don't need to hold all that information. You just need to filter in all the different parts. And then once you have the right information profile that you're looking for, when it happens, then you can record it happening and then say that it happened this way and this time and coordinate with the other information. You don't need to record everything. It can be just live streamed. And then, um, use Google's memory to hold all of it if you want. And then delete all of it every day and keep what you need.
It's maybe just decades away rather than millennia. Okay, so we build the detector, we detect the bar shift into a higher frequency level, and this coincides with a LIGO detection at the same frequency. Does that mean we've finally definitively detected a graviton? This is where things get a little muddy. If gravitons exist, then yes, the click was probably due to an actual graviton. But that's not the same thing as a formal discovery of gravitons, because there are ways that gravity could have made the click happen, even if gravitons don't exist at all. Now, to explain that, I want to go back to the phenomenon that started this whole forces as quantum fields business, the photoelectric effect, which is often described as providing proof of the existence of the photon. Take a pair of conducting plates with a gap between them and shine a laser at one plate. Energy from photons in the laser can be absorbed by electrons in the plate, allowing them to jump between the plates and resulting in a measurable current. Now apply a voltage across the gap, so the electrons need a minimum energy to make the crossing. Before we knew about photons, you might think that as long as the laser was bright enough, it could provide the needed energy to cause a current. But instead, we find that if the frequency of light is...
I'm feeling a lot of misinformation. The frequency has nothing to do with brightness. We don't talk about it like that. We talk about the amplitude. We talk about the wave form and its strength. Brightness is not about the wave form and its associated. We would never talk about it like this. No one talks about the brightness of the laser. They always refer to the frequency, the amplitude, the peaks and troughs, and the time between each peak and trough of the frequency of the light. Brightness is just more of the same thing, but if you don't have the right thing, you won't excite the electrons whatsoever. But no one says it like that. They just say you need this frequency. It gives this specific result.
Below a certain threshold, no electrons will jump the gap. It doesn't matter how bright you make the laser or how long you shine it for. Now, this makes...
And again, the photoelectric effect isn't about shooting electrons from one side to another. The photoelectric effect is about energy from light affecting the electrons to jump up in their own orbitals, staying in their orbitals, emitting light. You end up with certain light coming off. Electrons jumping off is a completely different frequency range and does happen, but is not the photoelectric effect in its entirety. It's just one component of it.
If we say that 1, the EM field of the laser is made of individual chunks, 2, those chunks have a specific energy defined by the frequency, and 3, an electron can absorb only a single chunk in order to make its jump between the plates. Low frequency light, no matter how intense, just doesn't contain photons with enough energy to cause a jump.
Photons with the right wiggle to make the thing go pop.
This is the line of reasoning usually used to explain why the photoelectric effect constitutes the discovery of the photon. This is...
No one says that.
Wrong.
No one says that.
The photoelectric effect is really the discovery of quantum energy levels in electrons. That's because there is a way for a purely classical EM field to deliver its energy to enable a quantum jump. A classical field is able to deliver that energy in arbitrarily small portions. It doesn't do this by delivering tiny bits of energy over time, but rather by slowly increasing the quantum probability of a jump. It's technical, but the point is that the photoelectric effect didn't really...
You have to realize that the electron is in all positions around an atom, and we're talking about quadrillion positions around an atom every second. So by shining a laser point at whatever beam you're doing towards the atom, you're guaranteed a jump at some interval where the actual lead electron gets to that point. So it takes a certain amount of time for an electron to actually go full circle around, but we're talking about a fraction of a second, a quadrillionth of a second. And if the electron is, say, heading off in a direction that is sideways for a bit, it's still going to take the entirety of the atom and end up where you're shining the beam within a second, and possibly a tenth of a second, hundredth, thousandth, millionth of a second. It's not relevant.
Constitute the discovery of photons, it discovered quantized energy levels in atoms. Okay, so why the tangent to the photoelectric effect? Because the same reasoning applies to our graviton experiment. The way I described it, a single graviton with the right frequency excites a phonon of the same frequency in the metal cylinder. But even if the gravitational field is not made of gravitons, if it's really classical, it can still excite that phonon by slowly increasing the excitation probability as long as it has the right frequency. Now, this is a subtle point. If gravitons exist, then the clicks from a resonant mass detector coinciding with the right gravitational wave are almost certainly graviton detections, which is amazing because we didn't need a planet-sized detector, but they don't prove that gravitons exist because there's another potential explanation. So how do we proceed? In the case of the photoelectric effect, we were able to prove the existence of photons with a much more sophisticated experiment that involved preparing the EM field so that it would be in a non-classical state, if it is indeed a non-classical field. If it is indeed a non-classical field. For example, extremely low intensity lasers so that the plate is hit by just very few photons at a time. Then you can tell from the distribution of energies of excited electrons whether the EM field is fundamentally quantized or smooth and classical. And so in principle, this can be done with gravitons too, except that now we're back to the realm of how the hell do we do this? There are no natural source of non-classical gravity, and certainly none of single gravitons. Now, we may still need to build a graviton source rather than relying on natural sources.
Why don't you just shine a light toward why don't you just, like, you could have a light intensity density that is concentrated enough that you make a black hole. That is a microgravity effect area. As long as you don't make a black hole that will actually expand, you could make that gravity tiny effect be something that's like something that will peak a bit of energy in a very minute gravitational wave. But again, we're already able to make sound with our freaking speakers and stuff. The motion of a speaker is, again, just another type of sound. So if you want to figure out gravity and you forget that gravity is sound, you're going to be running in circles forever. If you remember that gravity is just sound, it's just big, then you can make your big microphone and it will just work.
So, are we back to the drawing board? Not quite. Our detector did just get an insane upgrade, and so the burden of the challenge now seems to lie in the graviton source, and perhaps some unexpected result will show up. Or we could actually go back to the drawing board and get even cleverer. A recent paper by Ralph Schutzold proposes an optical Weber bar instead of a solid resonant mass. In this experiment, you use laser pulses in an interferometer-like geometry so that a passing gravitational wave can transfer a tiny but lasting amount of energy to the light, which then shows up as a measurable phase shift. Unlike LIGO, which reads out a phase change caused by changes in the arm lengths as the wave is passing, this scheme aims to convert the gravitational wave's time-dependent modulation into a permanent frequency and energy shift of the photons, and then amplify the resulting phase difference over a much longer period of time. In graviton language, that net energy exchange can be described as stimulated emission or absorption of gravitons by the light.
Basically, if you have a beam of light that is spread out to bounce back and forth, any phase discrimination, whatever else, any kind of wiggle that thing has, as it was bouncing through, Imagine if you had the the light just bouncing constantly through an entire area, and then when it finally ends up on the other side, you get all that information, and you have like multiple um, discriminating factors that tell you not only did something happen, but with light based precision, which is frick, 300 million per second, um, you would be able to tell when a bump happens in the beam so that you would be able to then remap if it happened at, for example, where is my button? For example, if it's bouncing and it happens that something interferes with it, you can tell whether or not it interferes at this point, this point, this point, or this point before it gets to the detector. All that information is stored there and can be reconstituted so that you know not only did something happen, but in the entire grid of the single laser, where it should be lost a lot, it is possible for it to still be found as to when it happened. And then if you can correspond the where and when all that information happened, you can then, again, spray that information into a computer for 3D graphics that gives you a constantly updating two-dimensional surface to start with. You could also have a three-dimensional surface, which would be better, and that gives you the entire structure of whatever graviton waves that you want through the entire system. With just one laser, it just takes a bit more processing, which at the rate of processing power that we have with some of these computers nowadays, starting to use light-based chips, you might be able to use discrepancies within even the tiny light-based chips as gravitational wave detectors. Or they would be able to um, be like secondary detectors. Anyway.
Right. An analogy of stimulated processes in quantum optics. So it's kind of like lasing the gravitational wave itself, although the effect is observed in the light, not in the gravitational waves. As with the resonant mass detector, the energy transfer alone wouldn't be enough to prove that gravity is quantized. But this scheme offers a way to at least see the signature of quantum gravity. If the light is prepared in a strongly non-classical state, then energy conservation ties the photon state to the gravitational field's own energy. And this could put the gravitational wave into an actual quantum superposition, which would reveal itself in aspects of the phase of the interferometer beam. And if a gravitational...
I felt a lot of gobbledygook in that. I don't want to explain just how much none of that made any goddamn sense and is completely irrelevant to any of it. Oh, some weird stuff about phase and stuff of superposition. But what the hell did he just say? It hurt my brain to hear it.
But this scheme offers a way to at least see the signature of quantum gravity. If the light is prepared in a strongly non-classical state, then energy conservation ties the photon state to the gravitational field's own energy. And this could put the gravitational wave into an actual quantum superposition.
No.
which would reveal itself in aspects of the phase of the interferometer beam.
The only thing you said correct. Wow, that's a lot of no. Oh my god. You don't. Oh god. Again, these laser beam detect discriminators are only speaker. They're only microphones, and that's it. You realize I had a set of earbuds that I put into the speaker jack. No, I put them into the microphone jack, and I was able to use a speaker, the earbud, as a microphone. That worked. It wasn't perfect, but it worked. So there are a lot of things that you can jerry-rig to just be able to detect vibrations of stuff. You don't need to be very complicated. You certainly don't. Energy conservation? What are you talking about? Superposition? Irrelevant? It's just noticing the damn thing move slightly. Like, be adjusted slightly. These adjustments can happen by the electromagnetic field having a slight fluctuation, which pushes the wave out of phase, not the wave of the laser beam using to be the detector out of phase. Now the gravity wave out of phase. You said a lot of nonsense just then, and I'm so sad.
And if a gravitational wave could be in a quantum superposition,
No.
then it must be quantum.
What the fuck is this?
It must be quantum. The baseline.
Listen, gravitational waves affect things on the quantum level. They affect every atom in the entire universe. The question is, how do we be able to detect these events? And again, a quantum particle of the supposed graviton is forgetting that everything in the universe can vibrate. And you don't need any specific particle to do the vibrating and to transmit everything. It's just everywhere. So, again, you just need to listen, discriminate, project, record. You're done. We got the image. It's great. It looks like an image. It's fantastic. That all comes from a bunch of linear information that is then spread out and understood to be redistributed in a two-dimensional plane from a single string of information, of lots of information. And even a three-dimensional type of idea can be gained from all of this. But, oh God. Even when a person who doesn't know what he's talking about listens to this, it's like, okay, that's a lot of stuff. He must know what he's talking about. For a person who actually knows what he's talking about and then is like, are you 12? Sorry. Like, are you... Where, where are you getting these informations from? Where are you trying to gain these types of bits of knowledge from? Is it papers? Who's making these phrases for you to say? Who's fact checking you? Who's like how are you failing on so many different degrees? Like you get in this video, the guy gets a D plus, if that, because he gets some information right, and then the majority, and it's not just him. Again, it's him. It's the base science that he got us all the information from, fact checkers that I'm sure exist, and people who should know what he should say, telling him what to say, that he should also discriminate and know what to say, still failing. And as a professional, I would prefer it to be. Now, I'm not a I'm more of an amateur, but him being supposed to be being a professional, I would hope for better coherentness, but or better like correctness for everything that you're trying to say. It's a whole thing.
Optical Weber bar might actually be feasible with present-day interferometric tools, while the genuinely quantum gravity-sensitive version demands a much more extreme quantum state preparation and readout, and is even further away than the resonant mass detector. So yeah, the universe wanted us to believe that we could never hope to glimpse the quantum nature of gravity.
Also, imagine instead of having a laser beam, you had satellite beams sending stuff back and forth. Information discrimination of what information we're supposed to be receiving and everything that can make it messed up. Imagine if we had that kind of sensitive equipment. You could make an array out in space just based off of our own information grid and just say, okay, well, all the stuff that we normally tune out and not send via the internet, we can be monitoring all of that for the differences. I mean, obviously, we don't want to be monitoring personal information, but we would be wanting to monitor just the sending of the information and back and forth, and what could be the change in all of the bits that we expect to see, those bits that we're having to correct for could be the signs of the gravitational waves that we're hoping to find, because all those signals are subject to gravitational waves just like anything else. So the entire internet grid can be incorporated to be a graviton detector. Are you thinking in those terms? No. I'm going to stop there. You get a like anyway. No, I'm not giving you a like. You don't deserve it. First of all, we tried to. You don't have any definitive answers. And that's all I have to say about that. You get a D plus. This is not new information. None of that is new. And even still, even if you have some bit of, oh, we made a new detection idea of the bars and stuff. Okay, so you did a journalism piece. You didn't actually find anything. You didn't actually do anything of value. And you also misspoke, so you get a D plus, and that's all I can give you. It's not enough, but you might as well have got enough because, like, presentation, who cares? Anyone can do a presentation, especially with your setup. It does not matter. I do not care. If you don't actually say something, like, and even if you said we found something, the best you can get is you did a piece that talks about current events. Wow. It's not revolutionary, it's not amazing, it's forgetting some things. Yeah, I can't give you a better grade than that. But, I mean, rewatch this video, hear what I said about the whole thing about the ways that you can have bigger detection systems and, like, literally using the entire power grid would be not as easy to do because there's so much noise. But imagine you had a system that can handle all of that noise. And, oh, there's like some tree landed on a power line. Maybe we want to know that information and know exactly where it is on the power line so we can then take it off the power line, which is less likely to happen. Nowadays, you'd think maybe, oh, there are some birds, they landed on the power line. It's going to have a little bit of phase kick. It's a lot of more noise than you ever want to think of. And then we can just still remove all of that and be very sophisticated and learn things about gravitational waves from the power lines themselves. Right? But if like you can do things with like more lasers or a laser grid, but amazing what they can accomplish with just two beams and then the recombine and all of the information of all the things because they're not detecting anything throughout the length of the thing, they're detecting it from the entire thing, and then its wobbles are noted in variations of what it is when it hits the detector plate. Like, it doesn't actually, like, you have to work backwards to find out where in the beam these ripples take place on a time scale, and because they are time dependent, it takes a certain amount of time for all this stuff to happen. You can make a discriminator to know exactly when these things happen. So if you make a larger grid, you could do the same trick with a longer beam that is doing a wider sweep, and then you would have the ability to have an entire large area of laser grid with the same beam, and it's just more information that you'd have to then figure out exactly when things happen, how it all happens. There would be multiple input of the same event on the same photon. So you would have to then know all the different types of ways that the frequencies can join together and do interference and do constructive and destructive interference and all these different things that make for the other end result frequency that you detect at the end of the beam that gives you all the information that you need of an entire large area. And it's not the size of like a warehouse, it's the size of a goddamn mile long tube that they had. And they still can figure out a lot of stuff from that, which is great. You're not looking for tiny little particles. Please stop it. It's not going to happen that way.